This is going to be lesson 7.2. Title is going to be Volumes by Slicing. Or sometimes they say volumes of a base. That's an alternate title. But before we even do this, we need to review a couple things, okay? So we need to review some basic geometry formula. Let's assume I have a side S, and from that I form a square. Okay, I need to know the area. Well, the area of the square obviously is just S squared. These you're going to need for reference, so you probably are going to write these down, okay? What if you had a side S, but this time you form an equilateral triangle? Well, using a little bit of trigonometry, knowing that this is 60-degree angle, and these are all congruent, you can actually show that it's square root of 3 over 4 S squared. Let's say you had a semicircle of side S. Well, full circle would be pi r squared. This one is 1/2 pi, and r is s over 2 squared. Okay. The other thing that's going to come up on the homework is what's called a right isosceles, and I'll let you think a little bit about what a right isosceles triangle is, what the area that is, and as a hint, that's going to be 45. Make sure you have these formulas written down in your notes. The idea behind volumes by slicing is the following. So far we've just added rectangles, which are two-dimensional shapes, but nothing is stopping us from adding three-dimensional shapes. So here's a situation where I have a circle, and I'm going to use this circle as the base for my shape, for my volume. Okay, so what I'm going to do is I'm going to lay it flat. Okay, so look at it again. Okay, so the circle is here. I want you to just pretend I'm laying it flat on the ground. Okay, so now it's flat on the ground. Coming out of the circle in this first case are going to be squares. So I want you to imagine that from each point along the circle on that chord, a square comes out. Well, if you add up all those little squares, it turns out that you're going to get a certain solid shape. Okay, so here's the shape that you're going to get. Eventually, you'll end up with that shape, and you can kind of see if you slice it, the cross sections are going to be squares. There's some smaller squares at the edge of the circle and some bigger squares at the center of the circle. Okay, so the question we want to address is how do we find the volume of this shape? For the first example, we'll just use that picture. I'm going to pick a radius of 5 as the base. So the equation of that circle is x squared plus y squared equals 25. Okay, and then the cross sections will be squares. Again, pause the podcast if you need to write it down. All right, so first things first, I'm going to draw in the xy plane my base. Okay, so here's the circle. There's a top half, and it turns out there's actually a bottom half, and there's a reason why I'm splitting it. Okay, because if you were to graph this on the graphing calculator, you would have to solve for y equals, and notice this one is y equals positive square root of 25 minus x squared, and then the green one at the bottom is going to be negative square root of 25 minus x squared. Okay. What we're going to do next is a little bit artistically difficult, so if you have trouble, you don't necessarily need to draw this in your notes. What I'm going to do is I'm going to try to draw it so that the y-axis is now laying flat. So the x-axis is just fine, but now the y-axis is going to be laying flat on the ground. Okay? And then we'll try to just draw the perspective of what that circle might look like if it was laying flat on the ground. That's terrible. Let's do it again. So it might look roughly like this. Okay. Now I want you to imagine that coming out of the circle along these chords are squares. So here's a square here. There might be a smaller square over here. Okay, but if you have enough of those squares, you're going to get the solid we see. We'll call that S. Well, where does that show up? That shows up here. We'll call that S. Just like the previous section, S is just going to be top minus bottom. That's why I stress these little dots. So it's going to be square root of 25 minus x squared, that's the top, minus negative square root of 25 minus x squared. Of course, you can just simplify that to be 2 times square root of 25 minus x squared. So that's our S. Let's take a little closer look at the square. Here's the square, side S. Okay, so I want to calculate the volume of the figure. What I'm going to do is I'm going to first calculate the area of the square, which is just s squared. I'm going to give the square a tiny, thin little thickness. Okay, and as we've seen in calculus, very thin things we call dx. So it's going to have a tiny thin little thickness dx, which shows up here. Barely see it there as a line. So the volume would be area times the little thickness, so s times dx. Well, that's pretty much all it is, because that's one square. To add up all the squares to get the volume, we use the integral, because the integral is going to sum up all the squares. So it's going to add the square from here, to the square from there, to the square from there, and eventually fill up the whole space. I just need the bounds. It looks like I'm integrating from -5 to 5. So the final integral that you would have to figure out is -5 to 5 s, which is 2 to the square root of 25 minus x squared quantity squared dx, and you can find that on your calculator. The next problem we'll look at is the same situation. So my base is going to be a circle. I'm going to drop it flat, and what's going to come out of these circles instead are equilateral triangles. Okay, so we're going to just add up all these equilateral triangles, and eventually it's going to create a solid. Here goes. If you have enough of them, the solid will just look like this, and here are some of the triangles that's inside the solid. Okay, so it's the same idea as before. So let's take a look at the setup. Okay, so in this case, my base, I'll still keep it the same. It'll be the circle from example 1. Okay, but this time my cross-section will be equilateral triangles. Okay, so let's attempt to draw it. Okay, so here it is, and again, same circle, but instead coming out of the circle is now going to be equilateral triangles. So there might be a smaller equilateral triangle here, so on and so forth. General chord shows up there as s. Our s is still going to be the same, top minus bottom, which worked out to be 2 square root of 25 minus x squared. So let's take a closer look at our equilateral triangle. Looks like this. From before, we know the area of that is rad 3 over 4 s squared. I just need to give it a little bit of thickness. Again, in calculus, we call that thickness dx, so that's the volume. Here's dx here, if you don't remember. Dx is that thin little piece. And then to add up all the triangles, integrate from -5 to 5. You can use the symmetry and just integrate from 0 to 5 and double it if you want, okay? And s is the same before, and I'm assuming we can plug this in the calculator. The last example, I'm going to choose a different base. So in this case, the base will be the region between two curves, okay? So I'm just going to choose that the base is going to be the region between y equals square root of x, and the second one is going to be y equals x, okay? Cross sections, we'll pick semicircles, because we haven't used that before. Alright, so let's look at the picture. I'm going to exaggerate the square root graph a little bit, but we know it looks like this. And then I have the y equal to x graph, which we know looks like this. Okay, so there's this region in between, and that this region is going to become our base. So I'm going to draw it flat. This one's a bit of a tight fit, but again, we're just going to take little chords in between these 2 points, and coming out of those will be semicircles. Semicircle there, semicircle there, semicircle there. If you draw enough of them, it looks maybe like half a fish. Okay, so in this case, s is here. Okay, s again is just top minus bottom, so it's square root of x minus x in this case. Let's take a closer look at our semicircle. Here's our semicircle. The area of that is going to be 1/2 pi. S is here, so it's going to be s over 2 for the radius squared. I'm going to give the semicircle a little bit of a thickness. Dx, very thin. Dx is there. Dx shows up here again. And then I'm going to add up all the semicircles, integrate, and I can find the intersections algebraically 0, 0 to 1, 1. And I need the x1s, even though they're the same as the y's. So I'm going to integrate from 0 to 1. So the final integral you would have to do to figure this out is the integral from 0 to 1. I'm going to pull out the 1/2 and the pi, and then it's just going to be radical x minus x over 2 quantity squared dx. And you can also pull this out as a fourth later, or do this on your calculator. Okay, so on the homework, you only have 2 problems, but be warned that they have A, B, C, and D for one of them.